I know you're special.
I know what I'm not. You gotta study for the final exam.
That's right.
You gotta go back.
Okay, so let's talk a little bit about the final exam.
If you go back.
Most of the final exam will be based on chapters after 16. So I tested you on 8 through 16 today. Most of the final exam, a disproportionate amount, will be based on chapters 17 through 21. Now, probably what's going to happen is 21 is going to end up being extra credit, because we'll only get to that next week. So 17 through 20, so that would be 4 chapters, all right, will be the primary source of problems on the final. Now, I will have a few problems, all right, from chapters prior to that. Okay? So, I mean, some of the things, you know, I didn't have you compute the correlation on the previous exam. So I might do the following, and I put on the final, here's some values, tell me what the correlation is. You can have all those tables, which is partially filled out. You just have to fill in a few of the blanks and give you the final answer. Okay, that's typically what I do on the final. I'll pick up a few types of problems I missed on the first 2 exams, put those on the final, and then most of the questions will be based on 17 then through 20. Then probably what's going to happen is 21 will be extra credit. Okay? Not a lot of extra credit, but a little bit. Now, the other thing I'm going to do is develop. What do we do about homework for 17 through 20? I'm not going to commit to this absolutely totally today, but I think what I'll just have you do is bring your homework to the final. And what I would do probably is maybe pick a problem or so from the homework, and that will be part of the final. And you can just copy it from your homework to the final. Maybe 2 problems, maybe 3. Well, that's why you want to study between now and next week. And then, final week, I'll have office hours on Thursday night. Probably starting about 5:30 and running at least until 8, where I will be probably maybe out here in the vending area. All right? So you can come in at that time and ask me questions. All right, I'll send this out in email, but that's typically what I do on the final exam. I'll have one, pardon? Well, okay, Thursday before the final, I'll probably just be out here in the vending area. Yeah, you come here. No. I normally have a class Tuesday and Thursday, but that class has its final on Tuesday. So there's no class on Thursday. All right? So I come here instead, and I'll just answer questions. If you need to take a final early, I can give you the final at that time.
So homework is still 17 to 20?
Okay. I don't know for certain. That depends upon how far we get. But 21 usually ends up being maybe extra credit. Only if you want to learn 21. And only if you, I'll let you know next week. I'll be able to tell you exactly. That's typically what happens. 21 is the last part, and what do I do with it? Well, I think, well, why don't I make that extra credit? Give a little benefit to studying that last, giving that last measure of devotion. I know, it sounds terrible. Last full measure of devotion. Somehow that sounds like a speech from a long time ago. All right. So that's, I mean, that's how we'll finish out this class. most of the final exam will be based on 17 through 20. You'll bring your homework, okay? And you know what, here's what, you know, if you don't want to do any homework between now and then, that doesn't make sense to me, but what you could do is, I'll have a problem, you know, what I'll do is I'll probably have the problem statement written out. And if you didn't do the homework, you can take a whack at it and see what you can do with it. Okay, but I would suggest, all right, that you do the homework, or as much of it as you can, all right, because I will have problems on the final based on, again, 17 through 20. Again, 20 usually is, 21 is usually maybe a chapter too far, so what I do is I make that extra credit. Not a lot of extra credit, but a little bit.
The extra credit is based on homework too?
I don't know, we'll see.
If I could do it,
All right. So the questions on next. I mean, next week I'll have an exact set of statements. This will be basically what I've said today. Okay. All right, now, what I want to do is complete the rest of chapter 18. There's some important ideas here. In the previous example, that 23, where we looked at whether or not someone had rickets, all right, we sampled from a population and we either had success or failure, okay, and we counted the number of successes, all right. Again, that was 20%. Now, let's consider another example. So I have a population of students. All right, and I'm going to let X represent the score, exam score. Of a randomly selected student. Now, the random variable X has a mean and a standard deviation. So I'm going to write those symbols as mu and sigma. I might want to add in the subscript capital X to indicate it's associated with this random variable here. Now, in this case, we might be talking about, say, high school seniors who have to pass some sort of standardized test. I don't know if they do it when they're seniors, or is that when they do it, or maybe there was talk at one time. This changes so often, I never know what the final status is. But let's assume there's a test that a large number of students are going to take, all right? And the test has been standardized, been nicely refined. And the model we're going to think about here is the following. X represents the score of a randomly selected student. Now, if there's no homework problem, assuming we could test everyone, we could determine this value here, the mean over all students, and we could figure out the standard deviation over all students. Now, if we're talking about a standardized test and a large number of students, That might be very difficult to do, at least in advance. You can go out and, if you've got, in the state of Oregon, I don't know how many seniors, probably 100,000 seniors, maybe. That's a large population. In the model or the description I'm going to be, or models I'm going to use, I'm going to assume that these values exist. We could, in principle, determine them, even though we might not want to do that because of the expense. Now, suppose this is a new exam, a new standardized test. And we don't want to give it to everyone because we don't know how well the test is or how good it is. What we might do is the following, is we might randomly select maybe 30, maybe 100 students and have them take the exam, and we would compute their sample mean and their sample standard deviation. Okay? So what I might do is take a sample of size n. Typically, sample sizes are maybe like 25, 30, maybe 100, maybe 1,000. Okay? Now, from that sample, we compute a sample mean, and we compute a sample standard deviation. So this is the sample mean, and this is the sample standard deviation. Both of these values are random variables, because if I randomly select students, give them the test, I'll get two values. If I randomly select n more or n different students, I'll get different values. Those are random variables. Okay, now, we often assume the following. We often assume scores are normally distributed. So I'd write something like the following. X tilde, X has a normal distribution where the center is at mu and the standard deviation is sigma. In fact, they will often create exams that have this characteristic. Part of the reason it happens is probably has to do with humans, and there's some reason for this, but typical exam scores, ACTs, SATs, if we were to look at them and plot their histograms over a large number of students, we'd see this bell-shaped curve. Okay? All right, now, let's talk about this process from a theoretical point of view, or from a probability point of view. Let's see. In what I'm describing here, I'm taking a simple random sample of a random variable or from a population, but I'm getting n values. All right? The sample mean, one way of thinking about it is the following. It's the sum of the n observations divided by n. N, x bar, is a random variable. If I repeat this process, sample n values, x bar is going to vary. All right, now, another way of thinking about it is via this idea that I've been using. Imagine I have some sort of box. I push a button on it, and that in turn pushes a button on n copies of a device that produces random numbers. I add all of those results together, and I divide by n, and what I observe is the sample mean. Now, if you tell me the tables associated with this, or the densities associated with this, we can in principle figure out the densities or the table associated with the sample mean. I'm not saying that it's easy to do, I'm saying you could do that. So these are random variables. I can think of pushing a button on n copies of the same thing, getting results, adding them all together, dividing by n, and then what I observe is the sample mean. The sample mean is itself a random variable. It has a distribution or a table associated with it. It has a density. Okay. That's not nice. You're supposed to go to the next page. Now, the random variable x bar has a mean and it has a standard deviation. So over on the left, I'm using the notation. I have a subscript of x bar. X bar has a mean and it has a standard deviation. Now, x bar is from a simple random sample of size n. The mean of that random variable will be the mean of a single observation. Nothing terribly surprising there, but the standard deviation of the sample mean is the standard deviation of a single observation x divided by the square root of the sample size. What this means is when n is bigger than 1, this here is going to be smaller than just the standard deviation itself. In effect, what I'm saying is the sample mean, in general, will have less variability than a single observation. Why is that the case? Well, when I take n samples, some are going to be bigger than the mean, some are going to be less. They're going to tend to average out. These are theorems. We could call these theorems in math. And actually, I think we could figure them out from the rules I've already given you. But we'll just take them as facts. Well, let's go back to, oops. doesn't work. All right, now, suppose I have a random variable that has a normal distribution, or is described by a normal model, where the center is mu and the standard deviation is sigma. What is the description of the distribution of x bar? It's also normal. Same center, but the standard deviation is less. It's the standard deviation of a single observation divided by the square root of n. These are the values I had on the previous page. The new thing here is that x bar itself will also be bell-shaped. Now, the central limit theorem says, in effect, that result holds even when this is not the case in special circumstances, when n is big. When n is big, even if I'm sampling from a distribution which is not bell-shaped, it turns out that the sample mean itself will be approximately bell-shaped. We use that idea repeatedly in statistics. This result is exact when that assumption is correct, that I have observed n values from a random variable which is normally distributed. Here's a case in point. In this case, I have a random variable x, which is normally distributed. The center is at 10 and the standard deviation is 1. That was one choice. Over here, I have the distribution, or the density, if you will, of x bar from a sample of size 16. So I've taken 16 observations of this random variable, all right? And I'm describing here what I might expect to see in the sample mean. The sample mean will also have a center at 10, but the standard deviation will be this value right here divided by the square root of the sample size. The red is more tightly bunched around 10. If I look at a sample mean from 16 values, it's far more likely that that value will be close to 10 than if I look at a single value. A single value could range over all of this, whereas if I take the sample mean, it's far more likely to be between these, you know, where the curve, it looks like the curve touches the axis. I mean, I'm far more likely to get a value with a sample mean close to 10 than I will by taking one observation. And why is that the case again? And that's because, you see, if I take 16 values, looking at them individually, some will be bigger than 10, some will be less than 10, but when I average them, you're going to have the lows and the highs will tend to cancel out. So the sample mean has a far more compressed distribution as a rule. It's compressed by 1 over the square root of n. Okay, now, I stated that this result holds. This result holds even if I'm not sampling from a random variable which is bell-shaped. I'm going to illustrate that now using Excel. This is what we're going to do. Remember on your calculator, there's a little key or a little function called rand. And if you hit that button, it gives you some number between 0 and 1. The values that you observe are uniformly distributed between 0 and 1. There's no bell shape to the curve at all. Let me illustrate that by going back to one of my overheads here. This is not the best of overheads, but suppose I have a random variable which is I would write the following. X is uniform U over the interval from 0 to 1. Your calculator is such a device. It gives you numbers between 0 and 1. Now, the density curve goes from 0 on up to 1, and this distance is 1 unit. Basically, if you give me some value, say here and here, and I want to know what the probability is that I will observe a value between these two, all I have to do is figure out the area of this rectangle, and that will tell me the probability of observing a value between here and here. What would the width be? It'd be this minus that, and this height is 1. So this device here can be thought of having a uniform density or a uniform density curve, and I can figure out probabilities by just using areas of rectangles. I don't have to refer to a table such as I do when we use a normal model. Okay, now what I'm going to do is I'm going to generate a large number of these values, but I'm going to do it in Excel. And then what we're going to do is we're going to create probability or histograms of the actual data. And then what we're going to do is we're going to do this, it'll be a certain number of columns, a certain number of rows, and then we're going to look at the averages across the rows and see how those differ, if you will, those values differ from looking at individual observations. All right, so I'm going to invoke Excel, and we're going to be using the data analysis toolkit because it will generate random numbers for us very nicely. To do is I'm going to, let's see, what we want to do is we want to use the data analysis toolkit. And you can either follow me if you want or just watch what I do. I'll post this online after we're done. It's the concept that's more important than the actual details in Excel. So what I'm going to do, I'm going to click on the data analysis toolkit. And the tool I want to use is random number generation. So we'll do OK on that. Now this entry here tells the number of columns I want to fill up. And this represents the number of rows. So I think what I'll do is I'm going to do 30 columns. And let's do this across 100 rows. So basically, I'm going to be generating 3,000 values. I'll do it basically in an instant. Now, what I want, the distribution I want, is the uniform distribution. And I can select other values. Now here it says mean and standard deviation. Whoops, I don't want normal, I want uniform. First one, okay. Values between 0 and 1. So it's going to produce numbers just like this does. Okay. Okay, now, I'm going to tell it where I want this data put, so I click on this radio button here, and then I'm going to click on this and select a cell. I'll put it in A20, and so it'll go down and to the right. And then I do OK. And in an instant, I have 3,000 values, basically that I got from pushing a button on here 3,000 times. Okay, now, what I'm going to do is I'm going to create a histogram of these observed values. And so what I'm going to do is I'm going to create bins. And remember, there's a lower value and an upper value. Let me make this, I'll make it a little bit bigger here. So I have a lower value, and then I have an upper value. And to cover all the cases, all I have to do is have a series of bins that cover the interval from 0 to 1. Out of convenience, I'm going to go from 0 to 0.1, and then 0.1 to 0.2, all right? Oops, didn't get that right. And all I have to do is I can extend these down. I could type them in, but basically, all I'm going to do is ask Excel to figure out how many values down here are between 0 and 0.1, and between 0.1 and 0.2, and so forth. I'm going to count the number of values. Now, I have 30,000 values, not 30, 3,000 values. About 10% of them should be in each of the bins. So there ought to be a count of about 30. All right, now, to do the work for me, again, I'm going to use the Data Analysis Toolkit, and I'm going to use the Histogram Tool. And the way you use the Histogram Tool, first of all, it says input range. That's the numbers I want to analyze. So I'm going to do the following. We'll click on that. We'll select this cell right here, and we'll drag it down and to the right. All 100 rows or so. Eventually we'll get them all selected here. Okay, and then I want to make sure I get all the way to the right. Okay. Now the next thing I need to do is I need to tell Excel what the bins are. Now remember, this tool works by giving it the upper values, all right? It figures out what the lower values are. So I'm going to click on this icon here, and I'm going to drag it over these values. Now, I'm going to tell it where I want the output to be, so I'm going to click on this radio button where it says Output Range. And I think what we'll do is we're going to, as it jumps around, what I'll do is I'm going to put it right here in D1. So the data will go down and to the right. That's what the tool does. Now, I also want it to chart the output. That will be our histogram. And we do OK. And I'm going to clean up my histogram a little bit here, so it looks a little nicer. Let's see, frequency, which is the count, they're all about 300, and all the bars, which are the heights, they're pretty uniform. Let me improve on this just a little bit. I don't want any gap. I like a better solid fill. We'll make that white. And then we'll make the border color a solid black. And we'll make it a little thicker here. All right, there's my histogram. Fairly uniform. That's what I would expect. Okay, now, let's look at an average across a row. So this is what we do. I come over here, and I'll give myself one column of space here. What I'm going to do is I'm going to compute the average of every row. Now some of the numbers are going to be small, some of the numbers are going to be large, but average over 30 will be close to half. All right, so I type in average. And so I simply select that first row. So again, I have 30 columns. And let's see, if I do a close quote or close parentheses, the average was, for that first row, was 0.445, okay? Now I'm going to extend this formula down, and I'm going to end up with an average of every single row. I'll have 100 such values. Now if you look, most of these values are pretty close to 0.5. All right, now what I'm going to do here is I'm going to find the min and the max, or the minimum in that row and the maximum. The reason I'm going to do this is I want to construct a histogram. I don't want to use these same bins. I won't, I could, but I think it would be more useful to have a smaller bin size. So the minimum value, let's see, I want it on AF through 20 through AF 119. That's the range of cells. So the minimum value was about 0.388. Okay, what's the maximum? Well, again, it's max, that's a function. I want AF 20 colon AF 119. I could have selected this by dragging my cursor over the data, but I'm going to do it this way. It's a little quicker. All right, the maximum was 0.599. Okay, just to make sure I have the right column. Yes, it is AF. Okay, now let's create bins for this data. I think what I'm going to do here is the following. See, basically this is from about 0.4, a little bit less, to about 0.6. So what I'm going to do here is the following. My first bin will be from 0.35 on up to 0.4, and then 0.4 to 0.45. And again, I'm just going to extend these down to make sure that I cover all possible values. Now this is a relatively small number of bins. All I'm doing is I'm choosing this out of convenience. Maybe a choice of 10 would be better. My histogram will look a little bit different if I use 10 than if I use 6 here, I guess, or 5. Maybe I should correct that.
Is this chapter 9?
This is 18. I'm illustrating the ideas in 18. Actually, I'm going to change this. I'm going to change this to, let's make this, I'm going to make this 7.5. I'm going to make this, yeah, that's, okay. So this would be, and then this would be 0.425. And then I'm going to extend those. I'm going to have more bins, basically. Almost ran over my own data. Actually, I don't need these three here. That's okay. That's what I want. Okay, so what I've done, let me reformat these so they're a little easier to see. Okay. Now, what I'm doing now is the following. I'm going to create a histogram, not of all these values here. I'm going to create a histogram of the sample means. That average I computed on the right-hand side. I have 100 such values. Now, the central limit theorem is correct. This histogram should be roughly bell-shaped. Okay, now, so the first bin will be from 0.375 on to 0.4, and the next one is 0.4 to 0.425. So the bins have a width of 1/4. Or excuse me, how about not 1/4? How about 25 thousandths? Okay. These bins will cover all of these values in this table because the minimum in that column is 0.388, so it will be counted in here, and the maximum will be counted in here. I'm going to do it again now. I'm going to use the data analysis toolkit. So I click on that. I want to create a histogram, and then the data I want to use is over here in that right-hand column. So I have 100 values. The bins, the top values or the larger values are there. And what I want to do is I want to specify the output to the right there. It stops jumping around. We'll put that right here. And I want to chart the output, and I do OK. And I put the chart somewhere off the table, so we have to find for it, look for it. I thought I would be able to find that. Ah, right on top of it, sorry. Okay, what does that look like? Looks like a bell-shaped curve. And I'm going to clean this up again a little bit. get rid of the gaps, make the solid fill, make the border color black, and the style make it a little thicker. It's like a bell-shaped curve. That's what the central limit theorem is telling us, basically. Not exactly, but pretty close. If I look at the sample means, it's as though I'm sampling from a bell-shaped curve, not from a uniform curve. That's basically what the central limit theorem is saying. If you sample a large number of times, if n is big, the value of x bar looks as though it came from a bell-shaped curve. And that is irrespective. This is a uniform density. It has nothing, well, I didn't say nothing. You can have a lot of densities where if I look at the sample mean, it looks as though I've obtained a value from something that's bell-shaped. Okay, let's see here. So what I've done here basically is the following. I'm sorry, what? This is 107. It's prior to chapter 17. I didn't show this before. Now I've shown it. Yeah, end of 17. So what I've done is, when I look at the average, I've looked at a value that comes out of a device like this. Central limit theorem says x bar is going to be approximately bell-shaped if n is large. It's exact if I'm sampling from a population which is normally distributed. Here is an exact situation. This is x, that's the distribution of x. X bar is bell-shaped. I illustrated that in the case of a uniform distribution, you get approximately a bell shape when looking at the sample means. Sample mean has less variability than a single observation. The value of x bar is far more likely to be close to that center value than a single value itself. A single value can have a greater variability. Now, in looking at the data for the uniform distribution, all that I've done here is I've tried to illustrate the ideas associated with the central limit theorem. We would never do 100 samples of size 30 in an experiment. You would always combine it all together. The purpose here is just to illustrate what might have happened if we would have repeated sampling of size 30 100 times. What about the sample means? The sample means are approximately normally distributed. Now, we often assume something is normally distributed or something close to it. When that's the case, the central limit theorem is particularly good. Not everything is normally distributed. There are cases where that assumption breaks down. That comes from experience. For example, everyone got a lot of experience in 2008 when the financial system collapsed. The numbers were not normally distributed. They were seeing changes in financials over a given day that they weren't supposed to see in this version of the universe, as they would probably have said. Some things are not well modeled by a normal model. Sometimes the central limit theorem actually breaks down. and the financial data over a long enough period is an example where you have that breakdown. The central limit theorem is no longer applicable. Okay, I've talked about constructing confidence intervals. All right, and I went through, this is the formula. P hat is our estimate of the center, and then I add and subtract from it the margin of error. When I'm looking at sample proportions, this is how we compute the sample or the margin of error. I went through that process for the data involving the crickets. This quantity right here is referred to as the standard error. It's an estimate of this quantity here. That's all that it is. Now, sometimes you are in the following situation. You're going to sample from a population, you're going to count successes and count failures. And you want to create a big enough sample size so you end up with a specified margin of error. How big a sample size should you pick? These are three different formulas that can be used for selecting a sample size based on a specified margin of error, based on your confidence level, which will determine this special value of z. The difference in these formulas is on the right-hand side here. You almost never know what P and Q are, because you wouldn't want to do, I mean, why would you want to sample a population if you already know what P and Q are? These values might come from theory. That is a possibility. Or what you might have done is you might have done a sample before and have estimates of P hat and Q hat, and use those to then tell you how big a sample size should you select so as to obtain this margin of error that you specify. The worst case for size n is when both P and Q are 1/2. This will give you a sample size which will almost certainly guarantee that when you're all done computing the margin of error, it will be less than that you specified. So all of these will tell you how big a sample size to take to obtain a specified margin of error based on a given confidence level. So you can say, well, how many people should I poll to get a margin of error of, say, 3%? Well, it depends upon what you know. First of all, you have to have specified a confidence level, which specifies then your value C to Z star. You have to know what margin of error you're looking for, and then you use either this, this, or that as a kind of factor on the right. You use this in certain theoretical situations, very unusual. You would use this if you have some previous data, maybe estimates of what you think P hat and Q hat are going to be, or you can punt and say, I can just make this 1/4 and I'm guaranteed I will have a big enough sample size. Basically, you get these values of n by looking at that margin of error and solving for n. All right? And then when you get to the case where, well, if I already know what P is, why would I want to do a sample? Well, sometimes you have what you think is a theoretical value. All right? Sometimes you have some previous data that would suggest what P hat and Q hat are. And sometimes if you don't have any idea, then we'll call this the Hail Mary option, where you just don't know and you're going to cover all bases and you're going to pick a value of 1/4. All right, now. We're going to do one more thing and then we'll call it a day. I think we're going to do one more thing. do an experiment of flipping a coin. And we're going to look at that because that's a really nice example. And it's going to illustrate an important idea. So we're going to have an example of tossing a coin, we'll say 100 times. Now I'm going to write down the probability of a head is equal to 1/2, and the probability of a tail is 1/2. I'm going to call the first one little p and the other one q. Now, how do we know that the probability of the head is 1/2? Well, we actually don't. It's just a model. If you were to take something like this and flip it, okay, I think it's probably reasonable to think, well, I'm going to get about 50% heads, 50% tails. All right, well, there's a way of deciding whether or not that's a reasonable assumption. We can decide whether this is a reasonable assumption. What we do is we perform a test of hypotheses. Now, a test of hypotheses has a kind of certain structure or form. In a test of hypotheses, we have what's called the null hypothesis. And usually we write down the following. We use the capital letter H, a subscript of 0. Sometimes I'll say H0 and sometimes H0. Same thing. In this null hypothesis, P is equal to 1/2. Now, anytime I have a null hypothesis or a default, I need to have an alternative. There are several different possibilities here, and the alternative is sometimes referenced by using a subscript of A. In some texts, you might see a 1, H0 and H1. This is how we represent the alternative. Now, the alternative can be one, in this case, of 3 possibilities, but only one of these. You would pick one based upon your experience, maybe based upon what other people do. But let me illustrate how we would express those alternatives. One alternative is that P is greater than 1/2. One alternative would be that P is less than 1/2. And one alternative would be a kind of combination of these two, that P is not equal to 1/2. Now, in a test of hypotheses, we have a null and alternative hypothesis. Okay? We collect data. And compute a test statistic. In this case, what we would do is we would compute p hat, which would be the number of successes, or the number of heads, say, divided by the sample size. So this would be the number of heads, because I'm assuming that heads is success. That's indicated by the fact I'm using little p to represent its probability. And I divide that by the number of trials. I'm assuming that's 100. Now we compare this with the model based on the null hypothesis. Now, in this case, the model says p hat, the mean of p hat should be 1/2, and the standard deviation of p hat should be the square root of 1/2 times 1/2, all divided by 100. In other words, assuming that this is correct, this would be the center. P hat will vary, but p hat should be roughly close to 1/2. That's not very good. So our value of p hat will be approximately normal, centered at 1/2. And if I compute the standard deviation, that's going to be 1/20th. So the values of p hat, assuming the probability of a head is 1/2, ought to be centered around 1/2. Now, are there no circumstances under which I would reject this assumption? Well, there should be. I mean, if you have a coin and you can flip it 100 times and you can consistently give 25 heads, if you don't think that's a valuable coin, I do. Give it to me. I'll make some serious money on that. All right? Now, let's put some boundaries here and say over here. Let's assume that I'm using this as my alternative. I want to test to see, I don't have any knowledge of this coin, I don't know whether the probability should be bigger than 1/2 or less than 1/2. But if I observe a value of p hat that's too far to the right or too far to the left relative to where the center is, does it seem plausible I should say, maybe this is not right? If, on the other hand, suppose I test this versus this possibility. In that case, if I get a value that's too big, too much bigger than 1/2, again, I'll be in the same position. I'll say, this is probably not correct. Or if I'm interested in this as the alternative, if I get a value that's too small, I'm going to reject the null hypothesis. So in an experiment, to decide between whether or not a given assumption is correct, we perform what's called a test of hypotheses. We have a null hypothesis and an alternative, and the null and the alternative are always expressed in terms of a population parameter, p or mu or sigma, something like that. We go out and collect data, we compute a test statistic. In this case, it would be the number of heads divided by the sample size. And then we compare that result from what we would expect based upon the assumptions associated with this. The assumptions associated with the null hypothesis is that p hat should be approximately normal, centered at 1/2, and has a standard deviation of 1/20. Now, suppose we're interested in this here, right here, whether or not p is greater than 1/2. What I'm going to do here is the following. I'm going to take my center value and add to it 1.96 times the standard deviation. What that means is that this area right here is 2.5%. Now, if this is the null, and that's the alternative, what I've done here is this could be referred to as a critical value, which means if I observe a value of p hat bigger than this, and that's going to be approximately equal to, see, this would be 2 times 1/20th, that would be 1/10, so that would be about 0.6. If I observe a value of p hat bigger than this, I'm going to say, I'm going to reject my null hypothesis. Why did I pick this point here? That's somewhat arbitrary. This would be, this point here, having chosen 1.96, basically I'm using a level of significance of 2.5%. Sometimes you use 1%, sometimes you use 5%. Depending upon the level of significance, you end up with different what are called critical values, which is to establish a kind of cutoff point where you decide whether to retain the null hypothesis or to reject it. Okay.
You don't have to choose the confidence of 95%.
Okay.
90, 95.
That's right. Confidence levels in confidence intervals are related to levels of significance. We will get to that. In tests of hypotheses, we typically use either 5%, 2.5%, or maybe 1% for our level of significance. Those determine our critical values. Now this is what we're going to do next week. We're going to look more closely at this. These are the ideas from chapter 20, and I want you to start thinking about these ideas. This is a very good example, all right, because it's easy. We know about flipping coins. We think the probability of a head should be 1/2. If I get a value p hat, say that's either too big or too small, depending upon what I've chosen for my alternative, I may want to reject this. Now, does anyone know whether or not there's evidence against this here? Well, there actually is. You're actually slightly more likely, at least based upon what people have done, to get ahead than you are to get a tail. How do we know this? Well, there was a POW in World War II who was a mathematician. And POWs have lots of time on their hand. So he flipped the coin 10,000 times. All right? And he got statistically, what we would call statistically significant proportion above 1/2. You can actually set up devices that do this, and you can do it mechanically now. And I think people have done that and found the probability of getting ahead actually turns out to be probably a little bit bigger than 1/2. Okay? Now, if you want a fair coin, then what you want to do is you want a coin that has no sides to it, so to speak. I mean, most of our coins have what looks to be a head on one side and a tail. You'd want a coin that maybe is differentiated only by, say, the color. In which case, then the assumption of equally likely on each side would be more reasonable. You won't see deviations from this unless you do things 10,000 times. And if you have time to do flip the coin 10,000 times, you have way too much time on your hands. If you become a POW, I hope that you don't, then maybe you should replicate this and confirm this. All right. We'll pick up on this next week. And what I've done is I've started 20 as a kind of way of getting your mind to start thinking about test of hypotheses. Those are the two big things we do in this class: confidence intervals and test of hypotheses. All right. I'm done. I promise.
So
They're pulling me off the stage.
So based on what you do, are you able to do the homework based on this thing?
No, you won't be able. You can start looking at the homework, and you could read the text.
I know I will read that.
Okay. And I'll do a number of examples next week on 20. Right? Oh. Oh, you want to? Okay, yeah. Right?
This means, I'm not sure what this means, this space minus this, right? That's what symbol means.
That's the complement of B. There's nothing to do with it.
So, well, BC is not the space all around.
Well, okay, it is. There is an all around, but I don't think that's. You've included too much.
The complement of it?
That's the complement of B. The probability of the complement of B. You want to do some more work?